For 40 years, we knew the truth about Uranus. Dead planet, frozen core, no internal heat. The textbooks said so. The models confirmed it. Voyager 2 measured it directly in 1986. Case closed. Except now, we were wrong. Completely, catastrophically wrong. And the implications of that mistake? They're about to get a lot worse. Here's what every planetary scientist believed. When giant planets form, they trap primordial heat. Fire from their violent birth 4.5 billion years ago. That heat escapes slowly over eons. Jupiter glows with it. Saturn radiates it. Neptune burns with twice the energy it receives from the Sun. This isn't theory. It's observable fact. Measure the sunlight hitting a planet. Measure the energy radiating out. Compare them. If more energy comes out than goes in, there's heat inside. Simple physics. Worked for every giant planet we'd ever studied. Until Uranus. Voyager 2 flew past in 1986. Measured the heat flux. The reading, 0 excess energy. Meaning Uranus had cooled completely. Its internal fire had gone out. Alone among the giants, it was thermally dead. Scientists scrambled for explanations. Maybe it's ancient, billions of years older, cooled off while the others still burned. Maybe that massive collision that knocked it sideways also blasted its heat into space. But here's what nobody said out loud. What if the measurement was wrong? Because everything, every conclusion, every model, every assumption about Uranus for 40 years hung on one data point. One flyby, one measurement from a spacecraft screaming past at 50,000 miles per hour. One chance to get it right. 2025. Two independent teams decide to rebuild the calculation from scratch. They can't send a new probe. No mission exists. So they do something else. They build computer models pulling together 40 years of telescope data. Hubble images, ground observations from Hawaii, every scrap from Voyager. They model Uranus's atmosphere layer by layer, hazes, methane clouds, seasonal changes. Everything that affects how light scatters and heat escapes. Then they recalculate the energy budget. Sunlight in, reflected light out, heat radiated. The numbers shift. Wait, there's a gap. Energy coming out exceeds energy going in. 12.5% more. That's not measurement error. That's heat. Internal heat. But this doesn't solve the mystery. It detonates it. Because if Uranus has been emitting heat this entire time, and we missed it for 40 years, then what else did we miss? Now compare the numbers. Jupiter emits 113% more energy than it receives. Saturn, 139% more. Neptune, 162% more. Uranus, 12.5% more. Hold on. Rewind that. Neptune is farther from the Sun than Uranus. Receives less sunlight. Same size, same composition. Born from the same primordial disk. Yet Neptune radiates 13 times more internal heat. Two identical twins. One burns. One barely breathes. That's not just unusual. That's impossible. Something happened to Uranus that didn't happen to Neptune. Some event, some process. Something that either stole its heat or locked it away where we can't detect it. But what? The collision theory, that impact that flipped Uranus on its side. Maybe it blasted heat into space. Except, if an impact can do that, then our models of planetary formation are broken. Impacts should compress cores, generate more heat, not less. Or maybe there's a thermal barrier. Magnesium-rich layers deep inside forming insulation that traps heat beneath the surface. Heat exists. We just can't see it. But if that's true, then internal structure matters more than we thought. Size and composition aren't enough to predict a planet's evolution. Every answer generates a bigger problem. And here's the worst part. We're not just wrong about Uranus. Most exoplanets we've discovered are Uranus-sized. Ice giants like this, They're probably the most common large planets in the galaxy. We classify them by size, temperature, orbital distance, build models, predict atmospheres, estimate habitability. But those models assume we understand how ice giants work. And Uranus just proved we don't. If a planet in our own solar system, one we can observe directly, study up close, fooled us for 40 years, how many distant worlds have we misread? How many planets did we classify as dead that are actually alive? How many hot Neptunes aren't hot at all, just measured at the wrong time, under the wrong conditions? The Voyager flyby happened during a solar weather surge. The timing skewed everything. We caught Uranus at its coldest moment and assumed that was normal. One bad data point, 40 years of wrong conclusions. Thousands of exoplanets categorized using those conclusions. The error compounds, and we're only beginning to understand how deep it goes. Picture this. Uranus has 42-year seasons. Each pole faces the sun continuously for 42 years, then plunges into 42 years of darkness. Heat emission changes with those seasons. We measured it once, during one season, one moment in an 84-year orbit. Imagine trying to understand Earth's climate from a single day's measurement, then building 40 years of theory on that one day. That's what we did to Uranus. The planet's internal structure could be completely different from Neptune's. Its evolutionary history could be unique. That ancient collision might have consequences we haven't even considered. Or, and this is worse, maybe Uranus is normal. Maybe Neptune is the outlier. Maybe our entire framework for understanding planetary heat is backwards. Because the same physics governing Uranus governs every planet, including Earth, climate models, atmospheric evolution, temperature regulation over billions of years. If we're this wrong about a planet, we can study directly. How confident should we be about anything? And what do NASA intend to do next? NASA's Planetary Science Decadal Survey named a Uranus mission the highest priority for this decade. The Uranus Orbiter and Probe. Launch window, late 2020s, arrival, 2040s. Map the interior. Measure heat flow continuously across multiple seasons. Study that bizarre offset magnetic field. Answer the questions Voyager couldn't, but now those questions have multiplied. What's actually inside Uranus? Why is its heat signature so weak? Does the thermal barrier exist? How does a 42-year season affect internal dynamics? What happened in that collision? And the big one, if Uranus can hide its heat for 40 years, what else is it hiding? The mission just became more critical and more consequential, because we're not going back to confirm what we know. We're going back to discover how much we don't know. Every answer in science is supposed to narrow uncertainty. This one exploded it. Uranus has heat. That was supposed to solve the mystery. Instead, it revealed that the mystery was bigger than we imagined, that our models were broken, that 40 years of certainty was built on sand, and the planets we thought we understood, we're just beginning to realize how strange they actually are. Uranus isn't done surprising us. It's just getting started. If you're into mysteries like this, the kind where one discovery changes everything we thought we knew, hit subscribe. The universe keeps surprising us, and there's a lot more out there we haven't figured out yet.